So they say if I give you a rope which you and your friend is holding together, what do you think? Can you move independently or you have to move in a constrained way or in a restricted way? Constraint here means the restricted way of motion. So when you hold a rope, how will be your motion? Assuming the rope is taut always. What do you think?
So a restricted motion.
So it means your motion and the motion of the person holding the rope cannot be independent, right? So a taut rope will have tension, and tension is the manifestation that something is connected together. And therefore, everything which is connected together with the help of a rope, and the rope remains always taut. So when I say the rope remains always taut, is a condition, and this condition is essential to put constraint further. Now, in case of a rope or a string, there are certain conditions that we need to kind of assume or remember. Just Okay, guys, sorry. So in the constant relation, we have to think about, I mean, we have to carry some assumption in our head, and that assumption will let you understand why the constant has put in the first place. So the first constant we call the string constant. And in case of string, there is an assumption that we should remember, that string is inextensible. तो पहले बताओ कि string is inextensible. If the string is inextensible, so you can't increase the length, right? Isn't it?
Yes, sir.
And if you can't stretch the length, then the length is going to put a constant. So this is called the total length of string remains constant. That is total length of string remains constant. Now you will get many variety of question in this particular topic. So one is like a two block system or single string system, or you can say two block system with a direct connection of a string. So if I have two objects connected with a single string and it is not turning, twisting around any pulley, it is simply given to you. Okay. So when two objects are connected by a single piece of string, then the length cannot, change. It cannot increase, and we're not supposed to decrease, because we have to keep the rope always taut. Then only tension will be there, right? So imagine if I give you a piece of string, okay, and there are two friends who are trying to holding this end. The first friend is trying to walk like this. Second friend is trying to walk like this. You need to realize something, and the first friend is trying to walk with a speed v1 and second with a speed v2. Let's say this angle is alpha and this angle is beta, and this is your string. So the velocity can be resolved into two components, right? One component is along the string, so this will be how much? The component of velocity
V1
along
cos
the string,
alpha.
v1 cos alpha, and the component of v2 along the string,
V2 cos beta.
v2 cos beta. That's correct. So the v1 cos alpha and v2 cos beta will try to either stretch the string, or you can say loosen the string. There are two possibilities. But the first condition is that you have to keep the string always taut. And to keep the string always taut, the length must be conserved. I mean, length should not be decreased or cannot be increased because we have the fixed length. Now, the other component, let's talk about the other component as well. So the other component will be V1 sin alpha. Okay. And this component is, now you need to realize that what is the role of V1 sin alpha or V2 sin beta? Is it going to affect the length of string in any way? Is it going to stretch or compress?
No, sir.
No. So it is not going to do anything. So we should not be worried about the component which is not parallel to string. So the velocity component which is perpendicular to the string should not be taken care of. What we should only care about is the component which is trying, I mean, which is parallel to the string itself or along the string. Now, once you have this, diagram in your brain, in your mind, then you can answer things really easy. So imagine that at one time only one of the velocity is active, other velocity is like inactive. Tell me what V1 cos alpha will try to do. Will it try to stretch the string or shrink the string? What do you think?
Stretch.
Okay, and what V2 cos sorry, this is beta. Just a moment. So what V2 cos beta is trying to do, it is trying to stretch or come, or you can say shrink the string.
Shrink.
So now one is trying to elongate, other is trying to shrink, but we have to keep the length constant. Then the amount of shrink and the amount of elongation must be compensating each other, isn't it? So how are you going to keep the length constant? What is the simple thumb rule? So in time dt, how much v1 cos alpha will stretch? The answer is v1 cos alpha dt, right? In the same time, how much v2 cos beta will shrink? So v1 cos alpha in time dt will stretch by this amount, and v2 cos beta will shrink by this amount. To keep the length of the string constant, the increment of the length and the decrement of the length should be equal or to each other, isn't it? Hello, hello, hello. Tell me, guys.
Yes, sir.
How
Yes,
to
sir.
keep the length constant? That's a common sense. To keep the length constant, the factor by which it is trying to grow and the factor which is trying to, shrink, both must compensate, because we can't change the total length. So that is called the constraint. And because we have a mathematical relation, so we call constraint relation. So what is constraint relation? It is a simply it is an equation which connects or relates velocities of moving masses which are connected to each other by a taut string, or which are in contact with each other. So when bodies are moving in such a way to maintain their physical contact all the time, or if they are moving in such a way to keep the connected rope taut all the time, then the constraint will arise naturally, and therefore a relationship will also come into picture between the velocities or the displacements, and the relation of velocity and displacement is called constant relation. Constant relation is never written for acceleration. So this is a very common mistake that many should make. They write the constant for acceleration as well, but that may be the consequence of velocity. But the constant we write only for the actual physical movement, which is either displacement or velocity. Okay. So you may put a definition. What you can say, it is an equation relating either displacements oblique velocities of connected masses. Okay. And why it comes? Because the connecting mechanism, which could be a physical contact directly or by a help of a string, they do have their own constraint. So what is the constraint for the string? The string cannot be stretched, it cannot be extended, and that is putting a limitation. So the simple way of thinking is the one which is trying to grow the segment, the one which is trying to shrink the segment, must be counterbalancing each other. So we have to look at the segment, and what I have drawn, A, B, is called segment of string. So AB is called the string segment, and for every segment of a string, for every segment of string, the total or you can say the factor trying to extend the string must be counter balanced by factor trying to shrink the string. The string. Restaurant. Trying to shrink. Let me write it properly. I hope this is clear what I'm saying. So generally, how
Yes.
we solve question is we only look for the segment. So what is segment? You can see the rope is passing through various turns. So whenever a rope is turning, it will break the segment. One segment is a straight line. So if you see 10 straight line, there's 10 segments. If you see only one straight line, say there only one segment. If you see two straight line, there is two segments. And we have to look at the end of the segment, that how things will, get affected by the motion of, okay, the connecting masses, pulleys, and so on. So I'll show you one by one. So here the condition is simple. So for what is the constant relation here? V1 cos alpha is V2 cos beta. Is this clear? Hello, hello. Is this clear, guys? Tell me yes or no.
Yes,
Yes.
sir.
Okay. So imagine if we have a movable pulley. So we have a pulley which can move. And then there is a rope passing over a pulley. And these are the two ends. So let's say this end is trying to move with velocity v1, this end is trying to move with velocity v2. So both will shrink their respective segment or grow the segment. So how many segments we have? We have A, B, and let's call B dash and A dash. So how many segments you can see? Tell me guys, how many segments do you see? How many segment of rope do you see?
Two.
Two. Can you tell me the effect of motion of the end on each segment separately? So as the end A will move, it will affect the segment in some ways, whether it will extend or shrink.
Yes.
So it will shrink. And V2?
So shrink.
So what we do is, in such a question, you will see that the pulley, I have to move the pulley to keep the string taut, because unless pulley will not move, the string cannot be taut, isn't it? So let's say the pulley is moving with velocity v. Now, in your mental frame, try to create the subsequent motion of the pulley. So let's say pulley goes from here till here. Just move it slightly mentally. As a result of the motion of pulley, let's say the A and A dash are fixed. To make the pulley move by some value x, how much total stretch is required in the string? Can you guess? how much we must stretch the string as a whole to make this movement possible? If the pulley moves by x, then how much string will stretch? So the string needs a rope from both sides, right? X from here and X from here, both, right? Then only it can move, isn't it?
Yes, sir.
So to move the pulley by X, we need 2x rope. And the whole idea is simple. In case of pulley, what you are supposed to remember is the total length which you shrink, only half of that length will grow, or will move, will be moved by the pulley. So pulley can move only half of the total length which you shrink. Do you realize this fact? Pulley can only move half of the total length.
Yes, sir.
Yes or no?
Yes, sir.
So that is why the V1 and V2 will decrease the length of each segment. So V1 will decrease by the value at a, or you can say rate. So let me put a kind of a name of this method. Let's the ID method, and ID stands for the increment decrement method. Increment decrement method. So A will increase or decrease. The motion of A will increase or decrease.
Decrease.
So write minus, and the rate of decrement is called velocity. Velocity is the rate of change of displacement. So it is also the rate of change of decrement, right? So write minus V1. What about V2? Will it decrease or increase?
Decrease.
But to move the pulley by speed V, it will extend the rope at twice the rate, right? So motion of the pulley will increase the length of the string by how much value? 2V.
2x. Oh,
Yeah. So we can write in terms of velocity as 2V, right?
yes, sir.
Because the pulley is connected to both the segment. So motion of the pulley requires increment of both segment, right? So the total length of the string which will grow is at 2V rate, and V1, V2 is kind of decreasing the length by the rate V1 and V2 respectively. But we know that the total length of the string is constant. So this sum must be equal to how much? This sum must be equal to, can you guess? So one is increasing, other is decreasing. Sum must be
0.
0. Do you realize this? The sum must be 0? One is trying to grow, other is trying to grow. One is trying to grow and the rest two are trying to kind of shrink. But they must compensate each other because the total length is conserved, isn't it? Tell me, guys. Hello, hello, hello.
Yes,
Yes,
sir.
I got it.
So there is simple rule. If A will move by x1 and if A dash will move by x2, the pulley can only go ahead by half of the total length given by the string. So whatever length you decrease, only half of that can be moved by the pulley. And I think that is organically realizable. Can you realize this part? Okay, so I hope this is clear. So the rule is if you decrease the length by x1 and x2, the total length which you have, kind of shrunk, the pulley will have to move only the half of that value to make it taut. I hope you realize this. Yes or no? So the distance moved by pulley is how much? 2x. And all of this extra rope you will get from where? Are you guys realizing this? Yes or no?
Yes.
See, pulley will move by x. So it will stretch both the rope by 2x. I mean, x and x, which is net is 2x. And x1, x2 is like the length which they are giving individually. So the total given length to allow the pulley to move is half of what you give. So the x is always, and suddenly if you use this relation, you can say v is, but don't try to recall or remember this formula because I can change the scenario. So imagine a situation here. In this situation, I change the rule. So let's say this end. So this end is trying to move this way with a speed v1, but I am now pulling this end by v2. And it is also possible that this is going by the pulley itself is trying to move by speed v. So what do you think? What should be the relation between all these three? Tell me. Okay, sorry. So what was the answer, Siddhant? Uh, tell me. So how to relate all these three?
So minus V1 plus V2.
And what we will do, it will always increase, right? In this case.
Yes, sir.
Yes.
So it will increase at what rate? Twice its own velocity. The pulley will affect both segment at once, right?
Yes,
Isn't it? So it will increase at a rate of 2v. I think Prashansa is not able to realize this. Are you able to realize this part? Yes or no?
Sir, I didn't understand why it is 2V.
Yeah, you see, common sense. Imagine nothing is happening. Let's do not consider v1, v2. See, in constraint relation, it's very simple. At one, think about only one motion and keep everything as frozen, like freeze it. Imagine it's a rubber band. Think about it. So imagine it's a
So
rubber
we
band.
don't have to consider V1 and V2 when we are
Yeah.
calculating.
When you are thinking about the effect of every motion, think only one motion at once. In that way, you can actually master it easily, or you can visualize it easily. See, if everything is the kind of frozen, let's say it's the rubber band. If I pull the pull, let's say this is a ring, and if you pull the ring by a value 1 centimeter, what do you think? How much length you have grown for the entire rubber band? It's still not realizing.
So 2 centimeters.
So if something is moving at 1 centimeter per second, so it will stretch the rubber band at what rate? 2
2
centimeter per
times.
second.
Yeah.
So if the pulley is moving with a velocity v, it will stretch the string at a rate 2v.
Yes, sir.
You realize this now?
Yes, sir.
So v1 is decreasing, v2 is increasing, v is also increasing, but at a double rate. So the overall change should be 0 because it is not extensible, isn't it?
Yes, sir.
See, to get a mental picture, we all do all this, freezing thing. We kind of, freeze the other event and try to analyze the one event at once, because it is very difficult to understand the every event at once. So you have to, kind of break it, see, break, see, break, see, and then add all such event or subtract or add whatever, and you will get the answer. So here the answer is the V turns out to be
V1
V2
minus
minus
V2 by 2.
sorry, V1 minus V2 by 2, right?
Yes, sir.
So you can keep on changing this direction, and still, if you understand the basic nuance of solving, it's very easy. So as a beginner, I have seen that many students struggle with this part. And imagine if I give you a pulley, and this pulley is attached to a spring, actually, not a string. But the constraint will come there as well. And this you will see in the advanced question, not now. And this pulley is not massless, it is massive pulley. Okay. Imagine if I release the pulley. Okay, if I release the pulley. So pulley will go down because there is some extension in the spring K1 and K2, right? But we have different K value. So the elongation that will actually happen in the K1 and K2 will be different. So we have to say, let's say X2 is the extension in the K2 and X1 is the extension in K1. So let's say X2 is extension in spring 2. So tell me, if I believe or if I assume that the two springs have been extended by these values, what do you think? What will be the downfall of the pulley? How below the pulley can go? So I'm assuming the pulley can go by X. Can you relate the X, X1, X2? Tell me. If K2 goes down by X2, K1 goes down by X1. There is an extension. So what do you think? How much pulley can go down? Any
Sir,
guess?
x1 plus x2.
So x1 plus x2 plus 2x equal to 0.
All will be 2x. It will go down by the value half of the total length given to you. I'm extending the overall connection by x1 plus x2. Only half of this can be moved by the pulley, isn't it? Now this is not constraint, but yeah, this is kind of constraint for the, not for the motion, constraint for the displacement. So if you tell me that, okay, the spring has extended by these values, then it is very easy to find the what? Displacement of the pulley itself. Are you getting it? Yes or no? I mean, if you can visualize it organically, then let me know. Else, I will explain again.
Can you explain again?
So imagine there is no pulley. Okay. So you pull the left spring by x1, right with x2. So what is the total overall extension of the string? What is the overall extension of the string? Hello, hello.
Sir, X.
What is the overall
2x.
extension of this? No, no, no. What is the overall extension of the string given x1, x2? X is a different variable we are trying to relate. I'm asking if you stretch the first spring, second spring by x1, x2, what is the total extension you have brought to this diagram?
X1 plus X2.
If that is a stretch, mentally imagine how much you need to pull the pulley downward to merge the gap. Whenever pulley goes down, how much it extends the string? If pulley will go from here to here, do you realize that you need to extend both sides by x and x, right?
Yes.
Now my string is this way, no? So how much extension I have brought here? By simply moving x ahead, how much I have brought the extension? Tell me. By moving the pulley down with x, how much extension you have brought into the string? Tell me.
Sir, 2x.
So from where the 2x will be compensated?
Yes, sir, got it.
It is the x1, x2 which is giving you 2x, isn't it?
Yes.
Do we have any other way of getting it? Tell me. Is it possible to for the pulley to move without extending the springs? Yes or no? Hello, hello, hello. Tell me. Tell me, Prashanta, is it possible?
No, sir.
So see, you're not supposed to, there is nothing like a formula. I mean, many students, they try to, mug up a formula, which is generally taught by many faculties. What they do is they give you formula. That length of this is constant, right, this. No. Newton's laws of motion, everyone should learn organically. I mean, it should come to your brain naturally. And then later on develop the formula. I mean, formula should come. Formula is an abstract way to solve any question. But before you go to the phase of abstraction, you develop your intuition in a beginner. Abstraction is when you know that, okay, I cannot see that complex motion at once. And for that complex motion, you try to resort to the abstraction. Abstraction means a mathematical way to arrive at the answer without looking into the physical reality. You do not want to see the physical reality, and still you're getting the answer because the mathematics never goes wrong the way it is established. But as a beginner, that method I don't encourage to anyone. I mean, of course, that is there. I can tell you also. As a beginner, try to develop the natural process of learning. Is this clear what I'm saying? So do you realize this relation x equals to x1 plus x2 by 2? Tell me, person sir, is it clear to you? Yes or no? Hello, 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 hello. Is this clear?
Yes, sir.
Now I make a small change, a small twist to the story. And the change is, on one side we have only a string. Other side I attach a string. And again I have the pulley which is movable. Now, can we stretch the right segment of the string?
No,
No,
sir.
sir.
So we know that strings are inextensible. So you're not going to get anything from the right side. So if I say that the x elongates by x1, I mean x only, then how much mass will go down? If x is the only extension I'm getting, what do you expect the motion of the m? How much below it can go? Or think this way, if the pulley goes down, by x value, how much spring will elongate? Tell me. See, I have to simply move the pulley down by x. That's my question. So to move pulley down by x, how much spring must be extended? Tell me.
Sir, by X length only.
Think about it.
Or x1 by 2.
So pulley is going down with x. So how much we have to extend the wrapped length of string? Common sense. So the string is actually, this is passing over pulley. This string is going this way, which I haven't shown. Okay, this it is the same string, right? Do you realize this? It is the same string which is passing over the pulley and going to the other side. So it is not something new. Hello, tell me.
Sir, 2x length.
Very good. Prashant, tell me, it is clear, yes or no? See, you have to pull the pulley down by x. How much you see the extension you need in the wrapped string?
So 2x.
And that 2x will come from where?
So from both sides of the string.
But which side cannot give?
The right side.
So all will come from which side?
From the spring side.
So the spring must be extended by what value?
2x.
That's it. So a pull, a pulling, I mean pull force, I mean, sorry, the motion of the pulley by x will make the string elongate by 2x. Understood? And if it will elongate by 2x, what is the spring force it will create? 2kx, isn't it? Hello, hello, hello.
Yes, sir.
And the rule is when the spring is creating 2kx, the connected string will have same tension. So even T is actually here 2kx. So when you pull the pulley down by x, it will experience a force of 4kx upward. Hello, hello, hello. Understood?
Yes.
So if you do the mg, you can see that the net force you can write as either 4kx minus mg equals to mass into acceleration, or you can do the other way around those, depending on whether it's mg is bigger or 4kx is bigger. So of course, these kind of questions are not part of this chapter, but it is definitely part of constraint. It is definitely part of the chapter called simple harmonic motion. It is part of chapter called work, energy, power. But the constant relation we have to learn here is itself. It is clear? And now imagine a situation. So while you solve the question, you always come across such question that a pulley is having a string passing over it, but it is fixed. The other end, I mean, it's the same string. The other end is connected to a block. What you're looking is the top view. So it is kept on the floor. And someone is pulling this pulley with a speed V. Let's call V1. So the block will move ahead with some velocity V2, isn't it? What will be the relationship between V1 and V2?
So V1 is equal to 2V2.
Correct. See, V1 can only move because someone is giving the rope to move. And here the only giver is the V2, right? So VT will try to shrink the segment by minus V2. And V1 will grow by. And this must be 0. So you can think this way also. So V2 is this clear, guys? Tell me yes or no. Hello, hello. Is this clear? Is this clear? Yes or no? Tell
Yes,
me,
sir.
guys.
Yes, sir.
Okay. So don't worry. Let me give you some other question. So we will also see some advanced method, but let me give you some easy one first. Mm. Can you relate V1, V2?
So V2 is equal to 2V1.
It's the same thing. See, we need to, first of all, when you see a question like this, we generally tend to forget that which pulley is to be considered. You can see this pulley is movable pulley, right? But this pulley is fixed pulley. So the pulley constraint we apply for every pulley which is movable. If it is constant, I mean, if it is fixed, then of course the answer will be really simple. No need to do anything. Person that tell me, are you getting the answer? This V2 is 2V1.
Yes, sir.
So this V2 will come down to this point, right? Eventually. So if V2 will go down, if M2 is going down, it means the pulley P1 is going right with speed V2, isn't it? So it is similar question. It's not difficult. Hello, is this clear?
Yes, sir.
So imagine this question. So this pulley is kind of fixed or hanging from the ceiling. So if I name the pulley as P1, P2, P3, how many pulleys are movable and how many are fixed? The first thing.
So two movable, one fixed.
So which two are movable?
Two P3.
P2 and P3.
Very good. For every movable pulley, you can write the constraint relation. That's called the pulley constraint. And to start with, you can make some assumption. So let's say M1 will either go up or down. So tell me what you want to assume, up or down.
Up.
All right. So I'll stick to what you assume. Let's call up. Let's call this is V1. If M1 will go up, then M2 is bound to go down. So can you correlate the V1, V2 here? So you have to think about the pulley number one. See, imagine that if I take the M1 up, what will happen to the pulley P2? How it will move?
Even downwards.
It will move V1 downwards, right? So look at the right two of the right sides. The left of P2 below cannot move, right? So if P2 will go down with V1, at what rate P3 will go down? Okay, think about
So
organically.
V1.
Think about it. That's why I'm saying think about it.
Or 2v1.
Very good. If you move the pulley P2 down by some value, let's say X, in this case, you are kind of, shrinking the or, losing that string by 2x, isn't it?
Yes, sir.
Think this way, the reverse process. If this pulley comes here, how much string you kind of give extra? You give 2x. So P3 can actually move to 2x because the LHS cannot move. This is a fixed length of pulley string. Do you realize this?
Yes,
But
sir.
Yes, sir.
anyway, no need to do this, hard work. You can think, okay, this will go down with V1. We have two ends, 1 and 2. This end is moving with 0 velocity. This will move with down with some velocity V dash. Or let's call V. What is the relationship between V, V1 and 0? That's it. See, I have no idea how this moves. So I'm assuming this end will move with V. This end can't move because this is fixed to some surface. So this is 0. And the P2 is going down with V1 that we know. And we know how to correlate, right? So here V will grow or shrink. What V will do? What V will do?
So grow.
So you can add plus V. And what V1 will do? It will
Yes, sir.
shrink at twice its rate, right? But once you get the V, you know what P3 will happen. P3 will go down with. So now P3 will go down with 2V1. This end will do nothing. So how fast this end will go? Which is V2. So V2 will be 4V1, right? Hello.
Yes.
So now you can do the same analysis for P3, isn't it? And if you do the same thing for P3, what you will like? Tell me, Prasan sir, what you will like? Any guess?
So in the P2, I didn't understand why it was minus 2v1.
Tell me, as the pool will go down, it will stretch the segment or compress the segment or shrink the segment. Imagine it's like a rubber band. So as the pool will go down, the band will shrink, isn't it?
So how will it shrink?
Imagine it is very much stretched already, highly elongated now. See, you have to think this way. When you try to move, if this is the string, and if the pulley is here, if pulley will go like this, it will extend. If the pulley will go like this, it will take away
Shrink.
this length. So it's like, you retrace the length. So that's called shrink. I mean, it is not literally. This is only to understand the idea how the equation we have to write, like what is the effect going to be. It is not I'm stretching or shrinking. The length is changing continuously, but this is how we describe it. Are you getting it what I'm saying?
Yes, sir.
So you have to only think about the effect. Do not take it everything literally. You are taking everything literally, isn't it? And that is
Yes.
getting all the problem. This is just an idea that how to write the effect of a particular velocity. Okay.
Yes, sir.
So V will have what effect on this? See, V is only connected to this segment, right? So what V will do to the segment?
Elongate.
And V1?
Shrink.
And V1 will shrink both segment, right?
Yes, sir.
So that's why we are 2V1. It is clear now?
Yes, sir, got it.
So it's very easy. If you know that V1 will go up with M1, the P2 will go down with 2V1, P3 double of that 4V2, V1. And if P3 will go with 4V1, the V2 will go with. Okay, I think I have taken one extra. So V1, this is 2V1, this is 4V1. So here
So
V2 will,
V2 will be equal to 4v1.
yeah, that's it. It is clear?
Yes, sir.
Okay, later on I'll give you some other technique also. See, right now we are solving only with the help of single idea, which is called Pauli constraint. Okay. Now, if I give you a situation where things are really simple, like this. And this question we all have been solving, right? The famous Atwood machine, right? Now here, the pulley is movable or at rest.
At rest.
So if M2 will go down with V2 and M1 will go up with V1, and we know that the pulley is not moving at all, what will be the relation? So V1 will try to shrink or extend.
Shrink.
V2. And pulley will do nothing. Twice of 0, right? The pulley is at rest, so we can add 2V0, isn't it?
Yes, sir.
Yes, sir.
And that is why you get V1 equals V2. That's why we don't write all these things. I mean, we know both are going to be same always. It is common sense, but it is also a constraint itself. It is not common sense. I mean, of course it is, but your common sense has come from the concept of constraint. Understood what I'm saying? Hello, hello, hello. Look at this diagram. So these three pulleys are lifting a big plank. And the upper three pulleys are fixed to the ceiling. So of course, this pulley cannot move. So maybe the plank is made of thermocol. This may be made of iron. So don't take mass comparison with the size. So what will be the relation between their velocities? Any guess? Assume M1 is going down, M2 going up. Can you correlate? And you can do it mentally. I mean, it's so easy. Move it organically, move one of them and see what can be done. If M2 will go up, then all the three connected pulleys will go up. Yes or no? Hello, hello, hello. If M2 goes up, then all the connected pulleys will also go up.
Yes.
And all will kind of shrink the length together.
Yes.
So how many segment you affect at once? The motion of M2 affects how many segments? Can you count the segments? Okay, you don't see the segments.
Oh, 6.
6 segments, exactly. So it is going to shrink 6 segments, yes or no?
Yes, sir.
So it's done. Minus 6v2 equals to plus v1 equals to 0. That's it. Tell me guys, it is clear?
Yes, sir.
Is it difficult? Is it difficult, to be very honest? Tell me. See, you can easily see, no, I can see organically that it will string the segment. So this much string I have to, kind of pull by the M1. So M1 can pull the 6 times what V2 will go, right? Hello. Okay, can you see this? I mean, or I'm not saying do it by some formula, but if you can see it, it's really good. Hello.
Yes,
Yes,
sir.
sir.
So the V1 is 6V2, isn't it? In all these discussion which we have done, the velocity relation will also translate to acceleration relation, but it is not the case always. Okay. So you can see it's really simple. I mean, if you come across any question, see, I can tell you here. You know what will happen if M1 will move, P2 will move by the same way because they are connected by the simple add-wood machine kind of structure. But for P2, it's interesting. If P2 will move, the left will not move, so the right will move. All of the movement will go to the right, and P2 motion will make the right side move double speed. And if the right will move with double speed, so P3 will also move with that double speed, and so its right will move with its double speed. Can you see that organically? Hello. Are you guys able to see all these things
Yes, sir.
visually? I mean, without doing a lot of mathematics. So these kind of question, or you can say one variety of question, can you solve with ease if you simply understand the the nuance of motion. That's it. Tell me, person, so is this clear to you?
Yes, sir.
Are you sure?
Yes, sir.
Now, so far, what we have seen that only two things are moving. Only two masses are moving. Let's make it more masses into play. And now we have a pulley. And I'll give some simple way later on of solving question. But before you go to the abstraction, try to do it with organic method. Okay. So once I give you the formula, you all can stick to the formula. I know. So you will stop learning, which is not good. So we have M1, M2, M3, three masses. Think about the pulley P1, P2 one by one. Now for P1, the pulley is at rest or is in motion.
Rest.
And for any pulley at rest, the left and the right will move with the same speed in the opposite direction, isn't it?
Yes, sir.
Yes, sir.
So if I say that M1 is moving with velocity V1, can you easily say what will be the velocity of P2?
V1.
V1 downward, right? So P2 will go down with V1, isn't it?
Yes.
Yes.
But if you look at P2 carefully, the right and the left, both are movable. They are not fixed. None of them are fixed. So in that case, I have to make some assumption. I have to take, let's say, M2 goes down with V2 and M3 goes up with V3. I can choose whatever I want. So now you have three variables given to you. You can choose see, in fact, let me tell you, you're free to choose the direction also. No one will stop you because every direction will have its own interpretation. So eventually all will lead to the correct answer only. So given these variables, can you relate?
So minus 2v1 minus v3 plus v2 equals to 0.
Excellent. So minus 2v1 plus v2 minus v3 equals to 0. Am I right?
Yes, sir.
See, how easy is this? Is it difficult? No.
No.
So once you realize the process, you can play with the constraint. Let me do another example. Siddhant, are you done with this question? Are you okay with this question?
Yes, sir. Done.
Very good. So we have now three blocks. And in the chapter of laws of motion, the only thing difficult is constraint. If you can master constraint, then your chapter you have in a kind of total command. So someone is pulling the right side, rightmost side block, and which is interestingly connected with all these things, as you can see. So how many moving masses you have here? Can you count? Can you see the number of moving masses here?
Yes, sir. 3.
How many?
So 3.
It means we will have three separate acceleration, isn't it? So M1, M2, M3, how they will move? Can you guess what will be their motion direction? So who is the primary cause of motion? Which agent is creating the motion?
External force.
Yeah. So M2 will go.
On the right.
So let's call A2. How M1 will move?
Towards the right.
How M3 will move?
Towards the right.
So can you guys correlate all three, A1, A2, A3? So the motion of M2 will affect how many segment? I mean, you can take velocity, but luckily the acceleration relation will also be same here. So you may write velocity also. I mean, acceleration also. So tell me guys, how A2 will affect how many segment?
So 4.
And will it increase or decrease?
Increase.
So what you will write? How to write A2 here? Think as a velocity only. Don't worry. Hello, hello, hello. Tell me, what happened?
So minus 4v1.
A1 is connected to how many segment?
3.
3 segment. Very good. And it will shrink or extend.
Shrink.
So what you will write?
So plus
Come on,
3.
guys. Hey, shrink means what? Plus or minus?
So minus.
It's done. What are you saying?
Yes, sir, minus.
So how to write the question? Tell me, no? What should I write here? Tell me, person, sir. What should I write here?
So minus 3v1.
Yeah, minus 3v1, which is I can write A1 here. Then,
So how to relate the pulley length?
see, the pulley which is connected to the mass will be one pulley. So M2 can affect these two pulleys directly at once. So we only look for the segment getting affected due to the motion of the M2. So M2 will connect pulley and pulley will connect the segment. So you have to count the segment only. So M2 is connected to two pulleys, which in turn connecting four segment. Do you realize this?
Yes, so
So as a result of motion of M2, how many segment you are affecting?
4.
And each segment will get increased or decreased.
Increased.
So tell me how to write. See, we have to think of only segment. No, that's it. Hello, hello.
So but if we are taking A1 into consideration, then
Listen, listen. See, if you look carefully, this entire string is one single string. They are not two string. See, earlier the problem was the first string stops at P2, and then we have a separate string between M2 and M3. So when we have the strings in pieces, we have to write the constraint for each part of string separately. We can't do it for the entire thing at once. But luckily in this question, if you see, we have only one piece of string. Do you realize this?
yes, so 4A2
Yeah.
plus 4A2
And what about A3?
plus A3
Hmm.
plus so 2A3.
Hmm. You're
So
not
sorry,
realizing.
minus A3 because it is shrinking.
Very good. You have to understand the distinction that when to write what, because here, although we have three moving mass, but the connection is only one. In the previous case, we had three moving mass with two connection, and that's why the way of writing will change. Here I can write all segment effect at once, because every motion will affect on the same segment, isn't it?
Yes,
Yes.
sir.
So any difficult constraint relation can be written easily if we realize certain things like the segment, the number of strings, and if we have the strings more than one, we have to write it for each string part separate. But there is a better way of doing it also, which I'm going to show you now. But before that, I told you something that you should not use the acceleration to write the constant. It is velocity generally. But in most of the cases, we derive the acceleration relation from the velocity only by differentiating. Now I'll tell you the dot notation for differentiation. So when you differentiate something with respect to time, so in the engineering, you will see that the notation we use is dot. So we're at x dot, which means dx by dt. So it's convenient. V dot means, so basically x dot is basically v and v dot is basically a. Now, if you look at the relation, if I put a dot over it, you can see this would convert into. So most of the velocity relation can be directly converted into acceleration relation by simply differentiating with time. And we, for the sake of writing, we write the dot notation of differentiation. Is this clear?
Yes, sir.
But that is not always true. I mean, the conversion is not always easier. I mean, it is true, but not easier. So imagine a situation. I have a pole. And let's say there is a bangle. And a thread is kind of tied to the bangle. And it is passed over a pulley. And the other side of the rope is hanging some mass. The pulley is somehow fixed. Do not need not to worry how it is fixed. That's not your concern. So we have two masses, M1 m2. At some instant it is theta. At some instant it will have velocity v1. Okay. So what will be the relation between v1 and v2? Tell me.
So V2 is equal to V1 cos theta.
Yes, so same.
So here comes the interesting point. Is theta constant here?
No.
No, sir.
And that is why in such scenario, when theta comes as a variable, and if you differentiate, you can't differentiate v1, if you differentiate the v1 cos theta whole dot, which means this, the LHS is simple, it is, I can add a2 directly, but this is interesting. This is d by dt of, and so you have to use the product rule. And this will become minus sine theta d theta by dt is the chain rule, cos theta into a1. So you can see that what you would have expected that it will be similar to the velocity relation. We have additional term here, right? Which requires a separate evaluation. Okay. But this part is matching this part, but this is extra, right? Hello, tell me.
Yes.
Yes, sir.
So if theta is variable, the right term cannot be zero, and therefore the velocity relation will not translate into acceleration relation. It will come with some additional term. But there is one particular situation when the velocity relation translate into acceleration relation as well. Can you guess what? So that's called the, when, this is very, very important. This is the most crucial part. I mean, if you can really understand this part, the constant life is set. So when system is released from rest, when system is released from rest, what will happen? Tell me. When you release the system from rest, then V1, V2 all will be 0, right? So technically, if there is no V1 and there is no V2, isn't it? So if you release from the rest, what will happen? I am releasing at an instant when none of them were moving. So can we write V1, V2 equals to 0? Tell me yes or no. Hello, guys.
Yes, sir.
And therefore, at that particular instant, what will be the acceleration relation? Tell me.
K1 equal to A2 equal to 0.
A2 equals to A1 cos theta, right?
Yes, sir.
Isn't it?
Yes, sir.
So do you realize that many students, they always write the acceleration relation and they think that they are correct. They are correct because if you read any question of S.C. Verma or any other book, they clearly write, find the acceleration of system if it is released from rest. If it is released from rest. If it is released from rest. You know why they say? They say so that the constant relation meant for acceleration and the constant relation which we know from the velocity, because constant is only for the motion, not for the acceleration. Acceleration means tendency of motion. It is not actual motion, isn't it? So motion is velocity. Constant we write for motion, for velocity. We never write for acceleration. But because of the said assumption, the underlying assumption that system is released from rest, system is released from rest, even though most of the students, in fact 98%, 99%, they don't realize that they are writing constant for action which is wrong, they get correct answer. Do you realize what I'm saying?
Yes.
And if you realize, can you explain me like what is happening? So at the moment of release, the terms appearing will vanish, the additional term in the equation 1. I hope you can see that. It is clear?
Yes, sir.
You can do in many ways. I can show you something really interesting, something more fundamental. Are you enjoying this constant relation?
Yes,
Yes.
sir.
Are you truly understanding it without any burden of formula and all?
Yes,
Yes,
sir.
sir.
Very good. Imagine the same bangle example. I'm just doing the line. So let me do a simplified version. In time elementary time dt, this string will move like this. Isn't it? Very small displacement. How much? This was V1, right? Yeah. So this is V1 dt. Am I right? Hello, hello, hello.
Yes.
And it is such a small time that this angle or this angle, both we can take theta only, because theta is very small as of now, right? So when this will go from there to there, how much string it will, kind of lose? You can check here. It is this much. This much you only release. Do you realize this? And because this angle is theta, so how much you release? V1 dt cos theta, right? Okay, not getting it. Let me zoom this part. This is V1 dt. Because the green and the red lines are very close to each other. If I draw a perpendicular, I can clearly see the extra length, the length which is released. So how much length you release by virtue of your motion forward? So you released V1 dt cos theta, right? Isn't it? Hello, hello, hello. Are you getting this? And therefore, the green line will move down with the same value, isn't it? Because I have given this as V2, this is V2 dt. But V1 dt cos theta is actually V2 dt. And that's why you see the answer like this. So this is how we write the constraint, by keeping the length constant. Is this clear?
Yes, sir.
Yes.
So let's do some one challenging problem. And this is like kind of the most famous question of this chapter. These are like iconic problems, which you will see in every textbook.
So if we know the constraint method, then we can apply it to all the pulley questions, right?
Yeah. You can solve now. After that, once you know the constraint, you can solve every question of laws of motion. Isn't it?
Yes.
What else you need? You just need the constraint, no? The number of variables will grow, so you should know the relation between the variables. That's it. The rest is laws of motion only. Net force equals to mass into acceleration. That's it. So what is the relationship between V and U?
U is equal to V cos theta.
U equals to V cos theta is the right answer. Excellent. Yeah, Prasansa, do you realize this?
Yes, sir.
So which constraint you applied here, Siddhant?
Sir, like I wrote 2u is equal to 2v cos theta, and then
Okay, or you can also write that you basically you can write for one of the string, not both. Along the string, it must be same, right?
yes,
Isn't it? Along the string, it must be same. Okay. So let's solve this question. Find acceleration of M1. So you can try for a while, then I'll solve.
So is it given that it is released from rest?
No, it is clearly mentioned the U is constant, so the M2 is not at rest. And if M2 is not at rest, then M1 cannot be at rest, isn't it?
Yes.
But if U is constant, doesn't mean the other particle, the other mass will also be constant. Its velocity will vary actually. And why it will vary? Because of the theta. So how to use theta? Why B is given now? Think about it for a while, then I'll solve. So you draw the diagram, think for a while, see what you can write and get. And then you can match that how much you progressed in your thinking with the solution which I'll give. So constraint means you have to start with the velocity relation. And if nothing is given about M1, assume it, write it, differentiate it. Okay, do it. Okay, guys, tell me. So first of all, what is the constant relation? Leave aside the accession part. What is the constant relation? That's simple, I think. What is constant? Tell me. Hello, hello, hello. Hello, hello, hello.
So V cos theta equals to U.
So what is V here? And because I need acceleration of the mass m1, which is I think here. So the a1, which is let's call A, is dv by dt, right? That's the definition of acceleration from kinematics. Not a big deal. So you are supposed to differentiate this relation where u is constant. So we can say a equals to u. You can take it out, and the differentiation of sec will give you what? Sec theta tan theta into d theta by dt. And this is where you get stuck. How to get rid of d theta by dt? But the b is given for that reason itself. And you can think this length let that length as y. Okay. So to bring theta into picture, we have to write some relation between theta, this constant, and this y. So we can write tan theta equals to how much from triangle? It is b by y. So y is how much? B cot theta. So it is dy by dt minus b cosec. But how to write v? What is v basically? So as you go up, y will shrink. So the rate of shrinkage of y is the velocity v, right? And these two together will give you the relation v equals to b cosec square theta d theta by dt. So finally, I got a d theta by dt, which is how much? And now this you need to substitute here. So 1 and 2 implies we can say a equals to u sine upon cos square theta into v by b sine square theta. But what is v itself? The v itself is u sec theta, right? And v we can attach u by cos theta. So it becomes really nice u square by b tan cube theta. Do you realize this answer?
Yes.
So this will be the toughest question from constraint world. Okay. Not all question I am going to solve as of now. Definitely, I'll give you some homework which you will attempt first. And when you will come with a doubt, then I can solve. If you will go to those questions, definitely that will become doubt. And if you don't ask in doubt, your chance of learning those questions is gone. So that will make sure two things. First, you have attempted questions. And second, know that you didn't get those questions, so you will learn something new. So attempt, I'll share this PDF, just a moment. So this part is clear to all of you guys?
So can we attempt the constraint questions from
Yeah,
HC1?
definitely. Not only Surma, rather I have shared a PDF. From there, you will get a lot of question of constraint, and we'll love enjoying those solving those questions. Now I'll give you the missile, the most powerful weapon by which you can solve with ease, and it is applicable to every question. It is based on some like theory from the future chapter which I haven't taught you, and this theory says something really interesting. The base of this concept you will learn in work, energy, and power, but right now you just learn how to use it. So there is another method. And this is a really powerful method which can solve almost every question whichever you come across. But again, it will be difficult to apply as a beginner, but yeah, you should see at least once as of now. Then as you grow mature, you can digest all these things. So this is called, I mean, there is a concept called for any system, the total work done by constraint internal for any system, the total work done by internal constraint force is always zero. Now, when I say constraint force, so first of all, you need to have a basic, a hint about what is constraint force. So from your common experience, you can tell me that if I'll tell some name and you will tell me whether you think this force is putting some constraint or not. So a string which is taut, does it put constraint on a connected masses? Yes or no?
Yes, sir.
Okay. If you are trying to move one object over the other object, which is in physical contact, so to maintain the contact, there must be some constraint, yes or no?
Yes, sir.
If two masses are connected by a spring, which can extend and compress both, Will it put constraint on the connected mass? Yes or no?
Yes, sir.
How a spring can put constraint? Come on. I think you're taking that example, the pulley example. I'm asking if two masses are connected to the two ends of a spring. Can they move independently of each other? Yes or no?
Yes, sir. They
Can they
can move
move?
independently.
So it was, is it putting constraint or yes or
No,
no?
no constraints.
No. Is gravity putting constraint to walk, to run, to jump? Can you and your cousin move independently on the road?
Yes,
So is gravity posing some constraint? Between you two?
no, sir.
So gravity is constant force or non-constant force? What do you think?
The
Non-constraint.
non-constraint.
Always remember gravity is non, spring is non. There are only two forces which are constant force. One is called the normal reaction. Second is called the static friction, and third is called tension. There is nothing else. So in the world of constraint, there is something called constraint force. And these are a pretty advanced concept. Try to understand this carefully. So we have only three forces which comes in this category. Of course, I'll put tension force. Tension is only talked about when it is taught. If it is not taught, there is no concept of tension. Second is static friction, when there is no relative motion. So that itself is constant. When you walk, you are not slipping on the ground because there is a constraint. But when you skid, there is no constraint. So the kinetic friction is not constant, but the static one is constraint. And the third is called the normal reaction arises due to the contact between two surfaces. No contact, no normal. And to maintain the contact, to maintain the contact throughout the journey, the motion, the normal will impose certain regulation, certain restriction, and therefore it will also bring the another variety of constraint called generally it is called the wedge constraint in the chapter of laws of motion. It's very famous because generally we use for the wedge and the cylinder. So because of that usage, it has taken a name wedge constant, but it is actually a constant posed by the surface contact force acting in the normal direction. So let's say if you try to walk on a hard concrete, so as you walk, do you make a dent in the concrete? As you walk on the floor, do you make a dent on the floor?
No, sir.
No,
Or do
sir.
you remain on the floor? Tell me. Hello, hello, hello. So do you go inside the floor or you
No,
walk
sir.
on the floor?
Sir, on the floor.
So why you're not going to, getting into the floor? Who is stopping you?
So the normal reaction.
Who is stopping you? Tell me. Hello, hello, hello. Who is stopping you?
This is a normal reaction.
It is a normal action. So a rigid surface, when in contact with other rigid surface, their motion cannot happen in which direction? In which direction they can't move together? Can you move into the direction of normal? On a surface, how you move? Parallel to surface or into the surface?
Parallel.
So how you cannot move? Into. Not getting right. Can you move into the tiles?
No, sir.
So in which direction you can't move?
Downwards.
In the
Normal
direction.
to the no, normal to the surface.
Yes, sir.
So why you're not moving? Because normal is stopping you. So can we say the normal is putting a constraint that no one can move into the surface?
Yes, sir.
Related to the force, related to the other surface, not absolutely. So if I move into the surface must go down, isn't it? Then only I can move, isn't it? So when you are standing inside an elevator and the elevator goes down, imagine there is no gravity. As elevator will go down, let's say there is no the ceiling of elevator, you enter the elevator, you stand there, and the elevator goes down. Between you and the floor, the gap will grow with time, isn't it? Like you will be hanging there in the air, isn't it? But you move together with the elevator in general, isn't it? I'm not getting it. This is the elevator. Yeah, it's standing here. Imagine there is no gravity. So as the elevator will go down, there will be gap between your foot and the surface here, isn't it?
Yes, sir.
So how much gap you create? Let's say you create a gap of 10 meters. So to remain in contact, the man must move how much? Exactly 10 meters, isn't it? Tell me yes or no.
Yes, sir.
Hello, guys.
Yes, sir.
So normal is putting constraint, which means two surfaces, when they touch each other, they can't dent each other. So if one will go, the other will also move to cover the gap, so that the two surfaces maintain their contact throughout the journey. So keeping the contact all the time is like a constraint. And such constraint we call wedge constraint. It is clear?
Yes, sir.
Similarly, the static friction when you walk, your sole of the shoe or the slipper doesn't slip. It remains intact there. Then you lift the other leg forward, you put it back. But then again, that foot will be stick to the ground. It will not move relatively. And you repeat the process. So the force which is stopping your foot is the friction force. Understood? So the force which is kind of stopping is the friction force. And therefore it is acting as a constraint, but you're not worried about it. So tension force and normal extension are constant, and the rule says that how we define the work? F dot dx, F dot dr, right? From vector, this relation W equals to F dot dr, yes or no?
Yes, sir.
So if W is equals to F dot dr, so work done by tension can be written as T dot dr. Work done by normal can be written as N dot dr. Hello, yes or no?
Yes, sir.
So working, okay, if I write elementary work, the elementary work by tension is simply T dot dr. So rate of doing work is called power. Yes or no? So this is called power by definition. The power is equals to T dot, and what is dr dt called? V, velocity. Sorry. So T dot V, which is nothing but the power, which is the rate of doing work. If work is zero, then power is also going to be zero, isn't it? So what this relation says that the summation of the tension acting on the moving mass or the endpoints of the string and the dot with their velocity direction of the endpoints. If you do it for the every moving part of the connected masses, it must turn out to be zero. I know you haven't understood this very much. I mean, it is difficult to digest as of now. But remember two things, that T dot V is zero, no matter what. And if you remember this, your life will be really sorted. Similarly, there's a relation called N dot V is also zero. And these two methods are the backbone of solving any challenging problem with ease. It is clear?
Yes, sir.
All right. So I hope this is clear to all of you.
Yes.
So what I'll do is I'll just revisit these problems which I have already solved to demonstrate how to use this. Okay. So I will not draw the diagram once again. I'll just do it in the corner in a small part and see how we can solve. Okay. So for that, you have to draw the mentally the ABD, the free body diagram. And if you can do so, you can get the answer. So the tension on the M1 will act like this, right? So what is the angle between the tension and the velocity of the M1? Angle is theta. So A dot B we write as AB cos theta, right? Okay, you don't remember this, the dot product. What is A dot B?
Yes.
So what is T dot V? What is the angle between the tension and the U for the M2?
180 degrees.
So we can just write minus TU because the dot will be negative, right?
Yes, sir.
And this must be zero because the net work done is, I mean, the net T dot V summation is zero on a system. And we're done. See, we got the answer, right? Okay, let's see any other question. These are easy questions. Yeah, look at this question. If you do the tension force T, 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 T. This is the tension for the M1. This is also T, 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 T. Now look at this. For A1, what is the net tension force in its direction? For A1, you can see this is 3T. And the velocity is also right. For M3, it is towards right. And for M2, it is backward, minus 40. And so you will get the same answer, right? Do you realize this? Maybe. Now this is really interesting. If I assume this tension is T, this is also T. But this will make this tension 2T, right?
Yes, sir.
So I can write 2T V1 minus T V2 minus plus T V3. And you can see the answer is same. So this is the abstract way of solving without thinking much. It is clear. So can you apply the same trick for any other question? And you can see that the benefit is you can solve any question. The rule is simple. Take tension in the direction of motion. Multiply with each other. And then write it for every moving part. And sum add up to 0. You will get the answer. Let me demonstrate by solving a even more challenging question than whatever we have solved so far. Now this goes really difficult. But if you can master this kind of question, you can play with the laws of motion chapter. So this is the wedge. You know wedge? A pulley is attached here. From this pulley we have a. So this wedge is also moving. We have block here. This thread goes this way. Connects to some another pulley. And goes back to the wedge again. But this pulley is kind of fixed. And the angle which is given is theta. As the block will start falling down, the wedge will go right or left? Okay, how wedge can move? In which direction the motion of wedge is possible? Can you tell me? In which direction the motion of wedge is possible, guys? Tell me.
You are right.
Right. So there is no way out, right? It is only way it can move is right. So let's say the acceleration of the wedge towards right is AX. How the block will move? Any guess?
Downwards.
Exact down?
So downwards and towards the right.
So it will move along with the wedge because of the constraint. This is again called normal constraint, but it will also go down. So the block will have two acceleration, which you don't realize because the wedge will anyway push because this is called the normal constraint. It will push it. I mean, it cannot go inside, so you have to go along. But it will also have the additional acceleration AY in the downward direction. Can you relate to AX now? Find a relation between Okay, anyone getting the answer? Siddhant, you got the answer?
Still trying, sir.
Okay. Okay, tell me, if you draw the ABD, the tension will be like this. But for the wedge, we have three tension T here. The pulley, upper pulley is part of the wedge, so we have to draw the tension there as well. And like this, because the pulley belongs to wedge. So force on the pulley is force on the wedge actually. So no need to do it separately. And therefore, if you look at the direction of motion of the wedge, what is the net tension force acting in the direction of the wedge motion? Tell me. So the net tension in the direction of wedge motion is how much? You can see
T
clearly.
plus V cos theta.
Very good. And what is that? Okay, now if this is done, then you can write like this: T1 plus cos theta into AX, because that's supporting. But for AY, you can see it's T AY because it's opposite, right? And this will give you the answer. The AY is AX1 plus cos theta.
So I
So
didn't understand why we subtracted TAY.
how the tension is acting for the small mass? Upward. And what is the direction of acceleration we have taken? Downwards. What is the angle? 180. So when we write T dot V, it will become negative, isn't it?
So, but we only take it in the direction of the wedge, right?
No, no, no. Direction of tension. We take the tension and the acceleration or the velocity direction of the object. So for small m, the acceleration is opposite of tension acting on the m. For capital M, the tension acting is much more, right? It is T plus T cos theta in the direction of AX, isn't it? Hello, hello, hello. Or there is a way of writing. You can say, you can name every vector T1, T2, T3, T4, whatever vector form, because they are having different direction. And then take the dot product. Okay. Okay, I'll come to this question again in the next lecture. Right now, I got some urgent. I mean, some rat has, kind of came to a wrong place, which can destroy many things. I have to remove him as of now. I mean, as soon as possible. So I'll continue this lecture in the